Hello everyone and welcome to another video. Today I'd like to continue our discussion on MATLAB and Simulink tools that can help you work with nonlinear models. In our last video we discussed how to use the linear analysis tool to generate trim and operating points for a nonlinear system. Please make sure you've watched this video because we're going to build off a lot of the results we generated in our discussion today. Now that we have these trim points, the natural next question is, how do I build a linear model of this nonlinear system about these trim points? In today's video, we're going to look at two different ways to go about doing this. First, we'll use the linear analysis tool again, and second, we'll use the linmod command. So, if all of this sounds like a lot of fun, let's jump over to the whiteboard and get started. Alright, so let's use the same planar vehicle model that we developed actually in this previous video. So again, if you're interested in the dynamics of this vehicle, please check out this vehicle for the full derivation of the equations of motion. But to refresh your memory, right, it was just this simple vehicle. You could think of it as like a boat which had both an axial thruster as well as rotational thrusters. So it could almost float around and spin on its axis if necessary or desired. So again, here were the dynamics. And what we did in our last video discussing trim points was we found 4 different trim points for this vehicle, or 4 different operating points. What I want to do now is look at 2 of them. I want to look at case number 1, or trim point number 1, and trim point number 4. And these two are very, very simple trim points, right? The first one was the vehicle just heading in the positive y direction at 15 meters a second. And we saw that here's the trim point that is consistent with this operating condition, right? We said the x and y position really didn't matter. We just arbitrarily set them to 10 and minus 10. But the x dot was 0, y dot was 15, the heading angle was 90 degrees, and the theta dot was 0. And in order to get that, it took 0.5625 throttle setting, I guess, on the axial thruster in order to get that, and it took 0 throttle setting in the moment, okay? Now, if you wanted to go slower at 10 meters a second, we found a second operating condition here, or a second trim point for that system, and we see that they are virtually identical. The only difference here is the y dot are obviously different, and since you're going slower here, you need less throttle, right, in order to achieve that, okay? So what I want to consider now is, now that we have these 2 operating points, really, that's all we need. We just need, theoretically, mathematically, right, all we need is the equations of motion, right, your nonlinear set of differential equations. That's right here, right? This is x dot is equal to f of xu, and then I need to think about, where do I want to linearize this function about? I want to linearize it about this x naught and this u naught. That's all we need to do the process, at least theoretically, right? So before we jump over to MATLAB, let's think about, what do we want to try to achieve out of this linearization process? So again, our planar vehicle model, if you remember earlier, we had our nonlinear planar vehicle, right? And we said there were 2 inputs to this. There was a U1 and a U2. Okay, and coming out of this was an entire state vector, I think, in our simulation. And then what we did is we hooked up like another block that would be able to compute some secondary parameters like the velocity, right? If you notice, the velocity is not one of the states. You have to compute the velocity by basically squaring this, adding it to this thing squared, and taking the square root of the 2 in order to get the velocity of the vehicle. So then we had another block here which computed something like velocity. Okay, so this was our nonlinear system. Right? So this was our dynamics over here. Here was a small little extra block to compute some secondary parameters. And now we have an operating point for this nonlinear system, okay? So now what I want to investigate is, how are we going to go ahead and, let's start simple. Let's get ourselves a transfer function. Maybe let's call it gv of s, right? Just between u1 and v. Okay, so what I want to do is I want to isolate how do the inputs or the effects of the axial thruster affect the velocity, right? So what we're going to do is we want to go from a nonlinear system to our linear system. Okay, and the process obviously is this process of linearization. Okay, now the question is, are there MATLAB and Simulink tools that will help us do this process? Now that we've done the work and we have a nonlinear Simulink model, and in our last video we discussed how to get the trim point, we should have enough to perform the linearization process. So that's the next step. Let's focus on just getting this transfer function between u1 and velocity, okay? So let's go ahead and first focus on maybe trim point 1, where we were trying to go 15 meters a second. So again, maybe you want to write down this trim point here to keep it in the back of your head, because we're actually going to run over to MATLAB right now and put this into a script and see what are the tools that we can use to perform this linearization process. All right, so here we are in MATLAB, and I've just started a little script, and you'll notice this looks almost identical to the script that we used when we were trying to trim the model, except now what we're trying to do is we're trying to linearize this model using both the linear analysis tool and linmod function. So to get that going, all we're going to do here is obviously define all the constants for my model, and then next let's go ahead and define the trim point that we're interested in. So I think we said the trim point, or the trim state, was 10, minus 10, 0, 15, pi over 2, and 0. And the trim control, as we just said, was 5, 6, 2, 5, and 0. Right? Okay, so if we go ahead and run this, we should have all of our constants as well as the trim state, x naught, and the trim control, u naught. Now, all we're going to need to do next is come to our Simulink model. Okay, so, whoops, that's the, that one. There we go. So here's the Simulink model that we set up last time. Now, what we need to do is get this thing ready to run using the trim state and the trim control as the initial condition and the input respectively. So I'm just going to go ahead and start with the initial condition. So I'll double click on my planar vehicle model, and I will plug in wherever I need for the initial condition, and I'm going to use x naught, right? That was what we defined over here. Okay, so now I have the initial condition set up, and now I need the trim input to this system. So that's over here. So I'll go ahead and delete these two out blocks. We don't need these. Let's go ahead and say delete. And now what I'm going to do is I'm going to grab a constant, okay? And the constant value is going to be u naught, okay? That was our trim input. And now I just need to hook it up here. So I'm just going to grab myself maybe a demux, and let's hook this up like such, and hook up the demux to the rest of the system. Okay, so at this point, here we go. I think the system should be ready to run at this point. So if I go ahead and hit play on this, we should be able to look at the scope and we see, yeah, this looks beautiful. The system stays at an x of 10, y just starts linearly increasing, x dot stays at 0, y dot stays at a perfect 15, theta stays at exactly 90 degrees, and theta dot is at 0. So right now, the system is running using the trim state and the trim control as the initial condition and the input respectively. And I'm just showing the inputs just to make sure we're all on the same page, right? The axial thrust stays at 0.5625, and we got 0 for the moment. So the model is set up and ready to run, or actually it is running with these trim points. So let's go ahead and take the next steps and figure out how can I linearize this system to get the transfer function between the thrust fraction here and the velocity of the vehicle down here. So to do that, what I'm going to do is I'm going to find the signal that I want to use as the input. So here it is. This is U1. And I'm going to right click on this, and I'm going to come down here to linear analysis points, and I'm going to set this as an input perturbation because this is the input of the transfer function or the linear system that I'm interested in. So when I click on this, you'll notice that Simulink will give the signal this little annotation or this little icon here to show you that this is going to be used for linearization eventually as an input point. Similarly, to get the output of the linear system or the transfer function that I'm interested in, I just come down to this signal, right? I want the velocity as to be the output of the system. And I will, again, right-click on that signal, linear analysis point, and now this is going to be an output measurement because that's the output of the system that I'm interested in measuring. And again, you see that icon come up. All right, so that's pretty much all we need to do to get the Simulink model ready. Let's go ahead and hit save. And now all we need to do is we are going to launch, again, the linear analysis tool to perform the linearization. So I'll come up here to my Simulink model, click on Analysis, Control Design, Linear Analysis. And again, the linear analysis tool is going to pop up in another window. Let me drag it over. All right, So what we can do now is, first, let's go ahead and come up here to Analysis IOs, and we're going to first click on this little drop down and make sure that it's set to Model IOs, because that's what we want to use as input and outputs, are these little signals that or the little annotations that we placed on the different signals. So again, yep, that's set. And just to kind of triple check, you can come down here and say Edit Model IOs. And what will show up is this little dialog, which will show you all of the available model inputs and outputs that you can use for input perturbations or output measurements. And you can see here that, yep, it's the thrust fraction as the input and the output is the velocity. So that's exactly the transfer function I want. I want the transfer function between u1 and vehicle velocity. Okay, that's great. The other thing that we may want to double check now is, let's also double check that the initial condition in the model is the actual trim point that we're interested in. So what I can do here is come here to operating point, and I'll just click on the drop down and come down here and say view model initial condition. And what that's going to give you is, again, a tiny little dialog that will say, here's the point where we're thinking about linearizing about. So you can see this looks exactly correct. And yeah, actually this doesn't have any inputs here, but it does have inputs in the Simulink model right here, right? It says you've got U0 coming into the system. So we've got the trim point correctly input to the system. So we are going to be going forward at 15 meters a second with the rest of these states as listed. So this is exactly the place that we want to linearize this system about. So to linearize this, it's actually really simple. You come up here and you can click on any of these. Here you can see it says linearize. You click on any of these and it will linearize the system and give you either a step, a Bloody plot, an impulse, Nyquist, whatever you're interested in. So, or if you kind of click down here, you can kind of find this button that says linearize with no plot. So if you don't want a plot, you feel free to just click this button. I think the plots are kind of nice, so let's just go ahead and click this button, and you're going to see that we're going to get a variable showing up here. There it is, linsys1, and then we're going to get a plot showing that linear system's step response. And here we go. So this is beautiful. You can see that this is the step response from thrust fraction, which was u1, to velocity. This is exactly what I'm looking for. So this linsys1 is the linear system that I'm interested in. The system has gone ahead, or Simulink has gone ahead and linearized the system for me. So again, you can just double click on this if you really want to see a little bit more information about it. This is fascinating. It looks like it's just a first order system. We'll take a look at that in a second to make sure that makes sense. But assuming that this looks reasonable, what we can do is let's go ahead and drag and drop this. Again, we see that it's here in the linear analysis workspace. I want it back in the MATLAB workspace so I can save it. So I'll grab, drag, drop it into the MATLAB workspace. And now when I come back to MATLAB and I look at linsys1, here it is. Here's the linearized system. So again, let's go ahead and maybe save this. I'll call it linear system 01.mat, and I'll save the linsys1 variable. Great. So it's saved here. What we may want to do is let's go ahead and get the transfer function of this system. So let's come here to our MATLAB script and say obtain the transfer function for the system. And actually, let me make this a cell. Okay, and what we'll do here is let's go ahead and get the A matrix. It's just going to be linsys1.A. The B matrix is going to be obviously linsys1.B, C, D. So we're going to do all of these. We're going to get all the A, B, C, and D matrices out of this thing. Okay, and then what we can do is let's go ahead and use our good old friend SS2TF to take this state space representation and turn it into a transfer function numerator denominator, and then we can go ahead and obtain the transfer function we want, which was GV, we called it, is transfer function of num den. Okay, and again, in this case, I don't think we're going to need to, but I always like to wrap these things in a minreal command. Again, if you need to refresh your memory on what minreal did, please check out this video here where we talked a little bit about pole zero cancellation and using the minreal function in MATLAB. I'll assume you've watched that and you know what this is doing. So I think we should be good to go. So let's just go ahead and evaluate this cell. So I can just go ahead and, where is it? I know it's shift, here it is, evaluate current section. Let's go ahead, Control Enter. here we go. So here's theoretically what the linearized system is between u1 and velocity. It's a first order system with a pole at minus 0.075. So maybe what we should do before we go any further is let's go back to the whiteboard and double check that this is reasonable. And if it is reasonable, we'll look at another way to numerically linearize this system. All right, so we just saw how you could use the linear analysis tool in MATLAB Simulink to perform this linearization operation. And we saw that at this operating point, or at this trim point, the linearized system was supposedly 1 over s plus 0.075, right? That was the answer we got from MATLAB Simulink. It was this first order system. Now, let's go ahead and check if that makes sense. So let's see if we can linearize this system analytically. So at this trim point, luckily the system is simple enough that we actually don't need a ton of machinery in place to perform this linearization. So what we can do here is let's basically realize that in this operating condition, it's effectively a one-dimensional system, right? Theta is constant at pi over 2, right? Because theta dot is 0. X is 0, x dot is 0, so there's not a lot of dynamics going on. The only dynamics is in the y direction here, right? So basically, let's just take our equation for y dot. So here is x, y, x dot, y dot. So here's the only place where there's any action occurring, right? So this was effectively saying y double dot, right, is equal to 1 over m fu sine of x5 minus fd sine of chi, right? That was our equation. Now, we can make a note here that, okay, again, at this operating condition, x5, right? We'll note here, what is x5? x5 was theta, right? And this is constant at 90 degrees, right? It's always going up at 90 degrees. So this is pi over 2, right? Similarly, chi, right? The course angle is the same thing as a heading angle in this case. So chi is also equal to pi over 2. So both these sine terms just go to 1. Right? So this gets a lot more simple. So we end up with, again, 1 over m times fu minus fd, right? Okay, let's remember, what was the axial force? So if you recall, fu was f max times u1, right? Times the first control input, right? That was how our model worked. And finally, what was drag? F drag, right? That was ct times v squared. That's what we ended up, okay? We can make one more substitution. If you notice, v is basically y dot in this case, right? So this is the same thing as ct times y dot squared, okay? So we can plug this in and we end up with 1 over m times f max times u1 minus ct y dot squared. Right? Okay. All right. Why don't we go ahead and distribute this 1 over m through? We can get this to look like basically y double dot is equal to f max over m times u1 minus ct over m y dot squared. Okay? So you can see that this is basically a second order differential equation in y. Or, you know what we can maybe do? Why don't we consider the state to be just y dot, to be the velocity, right? Because in that way, I can basically turn this into a first order differential equation. So in other words, let's go ahead and say, let the state, let's call the state, how about z, be y dot, okay? So if that's the case, you can rewrite this as, we're kind of running out of space. Maybe what we should do here is let's erase this up at the top. We'll start all over. Okay, so what I want to do is rewrite this using this state. So we end up with z dot, right, is just f max over m times u1 minus ct over m z squared. Great. So now this is a first order, but still nonlinear differential equation here. Okay, so what I want to do now is let's go ahead and linearize this about a given operating point. So to linearize analytically, right? We talked about this actually in one of our other videos where we talked about performing linearization via a Taylor series. You're basically doing a Taylor series expansion of this differential equation about the operating point that you're interested in. So the A matrix in this case was just your good old friend the Jacobian, right? So this was partial of, if we call this function f of z, right? This is now f of z. This is partial of f with respect to z evaluated at the point of interest, right? Evaluated at z naught and u naught, right? So this was just fancy words for partial with respect to z of this thing, right? F max over m times u1 minus ct over mz squared. And you evaluate the result here at z is equal to z naught and u is equal to u naught, right? About the expansion point that you're interested in. So taking this partial, it's pretty easy to see this doesn't contribute, but here, the 2 comes down. So we end up with this partial here is basically 2 ct over m times z evaluated at z naught. So turns into this, right? So here's your A matrix. It's really simple, okay? So your A matrix in this case is, oh, sorry, and be careful, careful. I dropped a minus sign, right? There should be a minus there. Okay? Your matrix should be negative 2 ct over mz naught, right? So again, this is an interesting point, but also it's probably expected. We notice here that the A matrix is a function of the trim point. In this case, this is our trim velocity. So in this case, we want z naught to be equal to, well, it's 15, right? That's the velocity that we're trimming about, right? That's our trim speed. So in this case, with z naught is equal to 15, and then all of these other constants, I think if you remember CT, the value we're using for that is, I think, wasn't it 1 over 40 or something? Yeah, 1/40th. And the mass we were using in this case was 10, right? So you can plug all of this in, and tell you what, let's wait to plug in all of these values here. Let's get the B matrix as well. So let's go ahead and erase this. Okay, so our B matrix in this case, it's a very similar expression, right? It was partial f, but now it's with respect to u, right? Z naught, u naught, right? That's how you get the B matrix. So again, it's just taking the partial of this thing, but now with respect to u. And now you can see this is actually pretty simple. This comes out to just f max over m, right? So your B matrix, in this case, your B matrix doesn't change. It's constant. It's not a function of the trim point, either the trim state nor the trim control, because you don't see Z naught or U naught show up here. So here's your B matrix, okay? And again, the only other difference we need here, the only constant we need is F max, right? So I think F max, what were we using in this case? It was also 10. There, okay? So now we can get the transfer function between z, which is velocity, right, and u1 here, okay? So the way we get that, right, is the transfer function gv. It's just our good old friend c si minus a inverse b plus d, right? And we're going to make a note here in this case, your C matrix is just 1, right, because the output of the system that I care about is just the state z. Where was it? I guess z. Well, z naught. The velocity, right? We said that was our fancy word for velocity. And then our D matrix is 0. So you plug in, here's your A matrix, here's your B matrix, here's your C matrix, here's your D matrix. Plug it into your expression, and what we'll end up with at the end of the day is, geez, where am I? I'm running out of space here. Yeah, let's see. Maybe I can erase this picture. We don't need this picture anymore. Okay, so what we end up with is GV of S is going to be F max over M all over S plus 2 CT over M times Z naught. Great. So now we're ready to go ahead and plug in all of these constants over here, right? Just plug in all these numbers into our expression over here, and lo and behold, what you end up with is 1 over S plus 0.075. So analytically, this is what the transfer function between U1 and velocity should be, right? which is beautiful because if we compare this with what the linear analysis tool gave us, they're bang on in this case, right? They're perfect. So that gives us confidence in what the linear analysis tool is doing. Let's go back over to MATLAB and see, is there another way or another set of tools we can use to also linearize it and see if it gives us this exact same answer. All right, so to linearize a system using linmod, let's go back to our Simulink model, and I'm actually going to save this as a second model here, just to illustrate that they are two different methods. So I'm going to call this planar vehicle model, maybe underscore linmod. Okay, so let's go ahead and clear these annotations just so we're not confused. So I'll go ahead and take away this, okay, and then let's also take away this linear analysis point. So again, just click on it again to get rid of it. Okay, now what we want to do with linmod is we are going to go ahead and grab some of these input and output blocks. So first, let's grab an import block, an in block, drag and drop it. And what I'm going to do here is we're going to use this as kind of the equivalent input perturbation signal. So what I want to do here is I'm going to, let's go ahead and delete this mux, and I'm going to stick this here. Okay, so now this is almost acting like that input perturbation annotation was in our previous method. So this is where we are going to input something, and now I want to make sure that the output is proper as well. So in this case, instead of it being a 2x1, I need to make sure I get the dimensions right. So this is now the second trim point for the second input, okay? So at this point, I think we're fairly set up on the inputs. Let's do a similar thing for the output. So now, actually, look at this. We already have these two outputs. Let me go ahead and actually disconnect this and delete this. And I will disconnect, and I'm going to hook this up like this, just so everything is consistent. Again, let's call this V. Okay, so now what we've got is we've got a system where this is the input and this is the output. Okay, so obviously this is not going to run right now because right now I don't know, you've got something very odd coming in. I actually don't know what Simulink decides to use here, but I think it uses 0. So if you run this, you can quickly see that we're not at equilibrium, right? The inputs, we're not sitting here at the trim condition, right? These inputs are both 0, and as such, the system responds like both of those are 0. But we're not trying to simulate the system. We're trying to linearize the system. So in order to do that, we've got the model set up and ready to go. I'll go ahead and hit save. Let's come back to our script. And now what I'm going to do is let's comment out this entire section here. Okay. And let's see if we can get the transfer function using another method. So we're going to go ahead and use the linmod command to do this. So I'm going to say help linmod. And you can see that what linmod does is it basically obtains linear models of systems of ordinary differential equations. That's exactly what we want to do. So what we're going to do is actually this version of linmod, where we're going to tell it where the Simulink model is, or where the nonlinear system of ordinary differential equations are, and we're going to tell it what is the state and control input, or the trim point that we want to linearize about. So the call is real simple. I just need to say linmod, and then what do we call this thing? Planar vehicle, I think I spelled that wrong. Vehicle model underscore linmod, okay, .slx. I can't remember. I'll tell you what, let's take off the file extension. I think there's sometimes where this thing doesn't like it. Okay, and then what is the trim input? It's x0. And what is the trim, what is the trim state? That's x0. And what is the trim input? u0. However, you got to be a little careful with u0 here, because u0 is basically the trim input to the system. If we come back to our planar vehicle model, right, we see there's only one input here, right? This is the only thing I want to perturb. So actually, this right now, u0 is a 2x1. I only want the first entry, right? I want u0 sub 1. This is the point. This is the trim point that I'm interested in linearizing about. And if it does this, this should give me A, B, C, and D. Right? Great. And actually, you know what? Maybe let me cut this, and we'll move this further down, because we're still going to want to do the exact same thing. It's just a different way of getting A, B, C, and D matrices for this system, right? Instead of using the linear analysis tool, we're going to just use the call to linmod. So it's really this simple. Now if we go ahead and run this, Well, oh, haha. Yep, I need this call too. Because I need to turn those A, B, and C, and D matrices into a numerator and denominator. So let's go ahead and run this again. And here we go. We get the exact same result. So we see that linmod gives us a very similar, well, actually, it gives us the exact same result. All right, so we just saw that both the linear analysis tool and linmod gave the same results in this case. So you might be asking yourself, is there any real differences? Well, I'm glad you thought about that, and you know what? MathWorks also is glad you thought about this because they already have some documentation on some of the differences. So if you come to this URL, I'll leave a link to this in the description of this video. You can see that they discuss some of the differences between using the linear analysis tool, which is effectively what they're calling Simulink control design linearization, versus what they're calling Simulink linearization, which is basically linmod. A little bit more if you're interested in digging a little bit deeper about linearization. There's also an excellent video by Brian Douglas. I'll link that as well, where he talks a little bit more about the inner workings about Simulink linearization. Okay, so with that being said, let's see if this changes if we look at the other trim point. All right, so to do the other trim point, I think we call that case number 4, right? Where all we need to do now is just change the trim point. So instead of going 50 meters a second, we want to go 10 meters a second. And now the control input dropped down to 25, or 0.25. So again, let's go ahead and do the exact same operation. So what we can do is, let's go ahead and maybe tell you what, let's put a breakpoint here, and we're just going to run this first bit because all I need again is I just need the trim point and the trim state and the trim control. And now let me exit out of the debugger. Let's go ahead and open up our Simulink model again. We already have our input perturbation and our output perturbation ready to go, so we're just going to go ahead and again start the linear analysis tool. And maybe what I should do is let's go and check the model initial conditions, make sure those are appropriate. Oh, and actually look at this. They're not, because this is the same session that I had loaded up earlier. Let's go ahead and hit the refresh button. Now we're talking. So as soon as I hit refresh, it got the new trim values from the model. So now I think what we're ready to do is trim again. So I can again come here and click on one of these, or you know what, let's just come here and linearize and don't do the step response. I'll just click linearize, and here we go. We get linsys2. And again, I'll grab, drag, and drop this into the MATLAB workspace where we can inspect it. linsys2. Here we go. It's a little bit different. So let's go ahead and again do this portion of the script. I'll uncomment this, and I guess I have to make this linsys2 now, right? And everything else is the same, so it's just a new A, B, C, D matrix. And if I evaluate this section, oops, I guess, sorry, I've got a breakpoint set up here. Let me exit out of this. Try this again. Evaluate this section. Oh, sorry, you know why? I haven't saved it. There we go. Save this. I'm just trying to execute all these commands. There we go. Here we go. We get a different transfer function. So again, this is interesting. It says that the transfer function changes, or the linearization changes depending on the operating condition. Again, let's go back to the board and double check that that makes sense.
All right, so I left most of this up because really the only difference between trim point 1 and trim point 4 was really the trim velocity here, right? So now this was 10 and this was 0.25, right? Okay, so all of this analysis, basically computing the Jacobians, everything was the same. The only difference was where do you evaluate that Jacobian, right? Instead of 15, you're evaluating this at a velocity of 10. So everything changes, and if you run this again, you plug in all those numbers, you do indeed come up with the same thing that we got in the linear analysis tool. Oh, well, I guess I should change this down here, right? This is what the linear analysis tool gave us, right? So everything is the same. And again, this is actually fascinating that this system is dynamics change depending on the operating point, which makes good sense if you think about the way this system is set up, right? We had this nonlinear term of drag, right? That's actually what's coming into play in this one-dimensional case where the vehicle is just going straight, right? We talked about this earlier, that the picture that went along with it, or where did my little boat go? Oh, here's my vehicle, right? When it was going straight up, we had the situation that at trim, that the force
from the axial control is going to have to equal the drag force, right? When this boat was moving at some sort of velocity v, right? So what's coming into play here is that this drag force, right, is nonlinear. If we were to plot F drag versus velocity, I think we're using a square function, right, a quadratic. So it looks something like this. And what we're doing now is trim point 1 was over here at 15 meters a second, and trim point number 4 is down here at 10 meters a second. So you can clearly see that the drag, its slope is effectively kind of what we're computing here. We're computing a linear model of the system at different locations. So because this slope changes depending on trim point, therefore your transfer function or your linear model changes with the trim point, which is clearly reflected in our Jacobian right here because you see that term show up in your A matrix. So again, all of this checks out. The analysis as well as the numerical tool seem to make sense. So just to close out this discussion on this single input, single output system, let's go back to MATLAB and verify that linmod gives us the same result.
All right, so to verify that linmod gives us the same result, again, it's really simple. We just need to use linmod to get our A, B, and C, D matrices instead of the linear analysis tool. So I'll just go ahead and uncomment this line. And you know what? We can just run this again because our planar vehicle model underscore linmod, this is already set up. So let's just go ahead and right click and, well, I guess now I'm going to learn. Let's save the script and right click and evaluate this section. And again, here we go. We get the exact same result. So this is perfect. We were able to show that the system is able to linearize about different operating conditions or different trim points. Now, we looked at just a CISO or a single input, single output case, but you know what? Multiple input, multiple output is just as easy. Let's quickly jump back to the whiteboard maybe and identify what type of inputs and what type of outputs we might be interested in.
So a multi-input, multi-output system is just as easy. So I've just gone ahead and erased the board and moved our diagram up to the top where we'd have a little bit more room. This is what we were looking at earlier, right? Getting the linear system between axial, throttle, and velocity, right, at a given operating point. Well, we can actually just add in more inputs and more outputs. So for example, what if we said, I want to understand how does the axial input force affect the heading angle of the vehicle, or theta. So you can just come in here and get yourself a demux, right? And there's a 1, 2, 3, 4, 5, 6 here, right? So I think we want number 5, right? This is theta, right? So what we could do now is we could start asking ourselves questions of, well, how does the axial thrust affect this output, right? And we could also look at different combinations. For example, like what if we wanted to understand how does the second input, right? The second input, which was this moment throttle setting, right? About how much moment is being applied to the vehicle. We could designate this as being an input. So now in this case, we've got 2 inputs and 2 outputs. So the linear system, I would expect to try to obtain either a single state space representation or 4 transfer functions, right? This would now be, I guess, maybe a better name or another name for this. This would be like a G11, right? And then we could also be asking ourselves, what is the transfer function between U1 and theta? This would be something like a G12, right? Or I could be looking at the transfer function between U2 and velocity, right? This would be like a G21. And then finally, what is U2 to theta, right? This would be like a G22. So we could be thinking about trying to generate now 4 separate transfer functions, or again, I guess 1 linear state space representation, however you like to think about it. But it's really simple to do this using the linear analysis tool. So why don't we go back to MATLAB and see how can we expand our CISO system into a MIMO system.
So it's quite easy to actually modify our system to have multiple inputs and multiple outputs for the linearization process. Again, let's just open up our Simulink model, and then we will just go ahead and designate this as a second input perturbation, and then we will designate theta here as a second output measurement. Great, there we go. So let's go ahead and save this and bring up our linear analysis tool, and let's go ahead and double check here that those were updated. So I'll come here in analysis IOs and edit model IOs, and there we go. This looks great. Looks like we've got both the U1, which was the thrust fraction, and U2 as the torque fraction as input perturbations, and then we have both velocity and theta as output measurements. You could hit refresh, I guess, if you want to be very certain that this did update and is synced up with the model, but it looked like this worked. So maybe let's also check that our initial conditions are proper. And yeah, it looks like we're still at the 10 meter per second condition here. So this was trim point number 4, I believe. All right, so I think we're ready to linearize. Here's kind of an odd error. If we go ahead and click on this button to try to re-linearize, we're going to get a little bit of an error here, saying that the plot size is basically incorrect, which is right. Instead of having just a single input and a single output, now we've got 2 inputs and 2 outputs. So now this single input, single output step graph we have here is not sufficient. So to get around this, all you got to do is just close this thing and then hit step again. And here we go. Now we've got multiple inputs and multiple outputs. And here's what's actually a little bit interesting. It looks like here the 1, 1 is actually between the thrust and theta. So as expected, this is kind of like a big 0 here. So it looks like it switched the numbering of the inputs and the outputs. So it looks like the first input is thrust. The second input is torque, but the first output is actually theta, and the second output is velocity here. So when we go ahead and take this linsys 4 and move it to the MATLAB workspace, we can see that's the case. So if we come here to the MATLAB workspace and look at linsys 4, let's take a look at this. All right, so maybe it's not as easy to see or not immediately obvious by just looking at the A, B, and C matrices because we actually don't know which way it was set up. But I think we can figure that out if we were to go ahead and modify our script down here where we are going to now, let's go ahead and get all of those transfer functions that we listed on the board. So I'll uncomment this section and we will comment this section out. Okay, so this is now changed to linsys 4. Okay, and now what we want to do is let's get all of those, the 1, 1 transfer function, which is between the first input and the first output, and I guess the D matrix needs to be appropriate, right? And then let's get the 1, 2, which is between, let me see, the 1, 2, that should be the first output, second input. There we go, something like that. Whoops. Okay, then let's get the 2, 1. So that is going to be between the second output and the first input. And then let's get the 2, 2 element, which is between the second input and the second output. Okay, great. So let's go ahead and maybe rename this as G11. Right? And let's do this for all of them. We'll get G11, we'll get G12, and then we'll get G21 and G22. Okay. All right. Great. So now if we go ahead and save and run this section here, what we'll see is those different transfer functions, and indeed, it looks like, yeah, G11 is 0, but G12, this looks like the transfer function now between the moment throttle setting and theta here. So we can see it's a second order system. And again, if we went through the same process on the board that we did earlier where we tried to analytically linearize the system, again, the system is simple enough and decoupled enough that you would get exactly this result. Now, G21, this is what we got earlier. So here is the transfer function between the the axial thrust throttle setting and the velocity of the system. And then finally, this is 0. So we actually see that these 2 inputs and 2 outputs, they're completely decoupled from each other at this operating condition. So again, we got to be a little bit careful that it looks like we weren't able to explicitly set the numbering of in terms of which was the first input, which was the second input, which was the first output, and which was the second output. So these numbering here in MATLAB is a little bit different from what we numbered on the whiteboard a second ago, but the results are the same. Okay, let's do the same thing for linmod. All right, so to do a similar thing for linmod, again, let's go ahead and open up our linmod model. Okay, and now all we're going to do is, again, make a similar modification. Now I'm going to delete this constant, and we're going to go ahead and grab another one of these input ports and hook it up. So now there's two inputs, both the thrust fraction and the torque fraction. And similarly, I'm going to grab another one of these output ports, copy, paste it here. This is now going to be theta, and I'll just hook it up to the theta signal, like such, save the model. And I think we're ready to go, so I will go ahead and come back to our MATLAB script, and maybe we will go ahead and comment this out. And then we will uncomment the linmod call. And now we're going to get our A, B, and C and D matrices using that other model and the linmod function. So again, let's save the script, and I'll right-click and run this selection. And, whoops. Oh, whoops. Yeah. Here we go. I messed up the linmod command here, right? The linmod command, again, if we look at our system. Wait, whoops, that's the wrong Simulink model. Sorry, let's open up the linmod model. Here we go. This is the linmod model. Here's what the error is. There are two inputs to this, right? So when I specify the trim point about which I want to linearize the system, I got to give it the proper state vector and then a control vector which has two inputs which correspond to these two, okay? So in this case, the trim point I want is like this, right? So U0, here it is. Yep, this is the proper setting. So now let's go ahead and save again and rerun this section. And there we go. So now, here, interestingly, now we've got the numbering correct. So again, if you bring up the Simulink model, we are able to explicitly, as soon as I bring up the Simulink model, right, we can clearly see that input 1 is the thrust fraction, input 2 is the torque fraction, and output 1 is the velocity, and output 2 is theta. So in this case, it looks like, yeah, G11, yes, this is between the first input and the first output, or the thrust fraction to velocity. G12 is the 12. Let me see, this is the first output. So this is velocity to moment fraction. So, yeah, it's decoupled. Similarly here, decoupled. And then G22 is the transfer function between the moment fraction and the angle theta. So, again, this looks great, and it's a couple of different ways now to get a linear system. All right, so we saw we got to be a little bit careful on the numbering here about which inputs and which outputs the system decides to call first, second, third, et cetera, et cetera. But we basically saw that at the end of the day, the transfer function that we obtained between the throttle input, or the axial thrust throttle, and velocity, right, at the condition here of, I think we were using, this was trim point 4, right, where the velocity was 10 meters per second. Right? At this condition, this transfer function turned out to be 1 over s plus 0.05. This guy between this was a big 0. There was no relationship there. This one also turned out to be a 0. And now the transfer function between the moment throttle setting here and theta was actually a second order system of 0.1 all over s squared plus 0.15 s. Okay, so that's what we obtained both through the numerical linearization process, aka the linear analysis tool, and linmod, as well as analytically, right? We showed that these are exactly what they should be. So the next question I'm sure you're asking is, all right, great, the tool gave us some linearized models. Are they actually accurate, right? Do they represent the real system? So in order to do that, what we should maybe do is let's go ahead and subject the nonlinear system to some inputs here, maybe some simple step inputs in these two commands, and then we will generate the same or equivalent step inputs to the linear systems, and just make sure that these two systems give us reasonable results as long as the system is operating near this trim point here of, well, I guess that's not the whole trim point, but
you get what I'm saying, right? At the condition of straight up at 10 meters per second. All right, so to check the reasonableness of these linearizations, I've just slightly modified the system we were using to linearize using the linear analysis tool. So I've added these green blocks, and as you can see, the green blocks are basically just the linear transfer functions that we computed using the linearization process. So here's GV and here's G theta. Again, these are for the trim condition of U0 and X naught corresponding to the 10 meter per second case, or that case number 4. So in the first case, let's just make sure, yeah, we're using a delta U2 of 0. So let's only perturb the thrust fraction and see what happens. So we'll feed the same perturbation to the linear model as well as to the nonlinear model. And again, keep in mind that I am accounting here properly for the difference between delta U and absolute U and delta X and absolute X. So again, if you want details on these discussions here, make sure you watch our video discussing analytical linearization. But long story short, these should be comparable. So what we're going to do right now is at time equals 1, let's just bump up the throttle by 2% here. Okay, so if we run this, and I go here and look at this scope, and I'll drag it over here to this side, you can see that these two are fairly reasonable. The yellow is the nonlinear simulation, and the blue is the linear simulation. So you can see they both agree fairly nicely. However, we do see that as the velocity increases, right, as you start moving away from that trim point, the nonlinear and the linear systems start to diverge. We can see this effect to be even more exaggerated if, for example, if we increase instead of just a 2% bump, how about a 50% increase in throttle? So we'll go from a throttle setting of 25% up to a throttle setting of 75%. And again, we'll hit run and check out the scope. And again, the linear simulation, which was the blue again, looks like this nice first order response. But the nonlinear simulation, which is the yellow line, right? That quadratic drag starts to really start influencing the system. So we see that the nonlinear system diverges significantly from the linear system, showing again that these systems are only reasonable in small regions near the operating point or the trim point. How about let's do the same for G theta. So again, let's turn off the delta U, and let's go ahead and turn on the bump in delta U2, which was the moment to the system. So here, we're going to increase this by 10%, okay? So here, if we go ahead and hit run, and now look at the theta component, let's go ahead and look at those. Here's what the transfer function says, and look at this. They're both right on top of each other. That's because actually this system is already linear in this dimension here. So the dynamics here between the U2 control input and the theta are actually already linear. So these two come out exactly correct, or exactly one on top of the other. And again, if we changed this now to go up by, I don't know, 0.75%, a giant jump in throttle setting, we see here that again, they're still right on top of each other, thus showing that the system is pretty much linear in this condition. So that's great. I think what this shows is both of these systems seem to work well. So these two linearizations that the linear analysis tool computed for us work very well. Again, be a little bit cautious here because this system was simple enough that there was actually no cross-coupling in the sense that GV and G theta at this operating point, linearly, they are not coupled. But we know that they definitely are coupled in some sense. So, for example, we can illustrate that real quick. Let's go back to our small input of just 10%, or, we could even make this smaller, 0.05, something small, like 0.05 here. So let's do this. Wait, sorry, what did I... yeah, there we go. Okay, 0.05. And let's go ahead and I'll turn both of these on. So let's do both of these at the same time. And I'll make this back to something small, like 0.1 in throttle. Okay, and now if we hit run, again, the theta is exactly perfect, right? Because those are linear dynamics. But now the velocity, if you look at this is very, very different, right? Again, the linear system predicts just nice first-order dynamics, but the nonlinear system, we clearly see some of the coupling between the states in a nonlinear sense coming in to give us this very interesting behavior of the nonlinear system. So again, you got to be a little bit careful about these linearizations and the areas in which they're accurate. But with that being said, I think this is a good spot to leave it. So just to recap what we talked about today, we looked at how to use two ways to linearize this nonlinear system, right? We started out with a nonlinear plant model, and we tried to now linearize it using both the linear analysis tool as well as the linmod function. And both give us very reasonable approximations and linearizations of the system about a specific operating point. Now, the next step in the process is, now that we have these linear systems, is obviously to try to build a controller using all of our linear system theory. The nice thing about these linear transfer functions, or the linear state space representation, is all of these tools that we built up can be brought to bear on this problem. We can do root locus, we can do full state feedback, we can do LQR, we can do any other types of number of control architectures and have guaranteed performance for the linear system, and then try to port that controller to control the nonlinear system. So that's where we're going to be heading next, so I hope I will catch you at one of these future discussions. If you've been a long-time subscriber to the channel, thanks so much for sticking with us. If you're new, please go ahead and consider subscribing, because we'll have lots of other discussions on control engineering in the future, and I hope to see you at one of these videos. See you later. Bye.